Dear students, hope you are well. Now we discuss multiple choice question 2023 metric spaces and complex analysis paper CC-13 semester 6 B.Sc Honours in Mathematics, University of Calcutta. Question paper 23 CC-13 question 1a. Which one of the following is not a metric on C01, where C01 is the collection of all real-valued continuous functions defined on the closed interval 0, 1, is not a metric. So this is not a metric. So this dxy equal to infimum 0 less than equal to t less than equal to 1 modulus of xt minus yt. Now to verify the triangle inequality, let xyz belongs to C01. Then for all t belongs to 0, 1 closed interval, we have dxz less than equal to dxy plus dyj. So dxz we actually verify for option 2. So infimum xt minus zt less than equal to infimum xt minus yt modulus of xt minus yt plus infimum of yt modulus of yt minus dt, where 0 less than equal to t less than equal to 1. Consider an example xt equal to 1. This xt equal to 1, this t-axis. So this xt equal to 1, yt equal to 40 plus 1, and this equation 40 plus 1, and z equal to 5, this equal to 5. Then infimum xt minus zd, this xt minus zd infimum is 0. Xt minus zd, sorry, zd is this. So sorry, x equal to 1, z equal to 5. So infimum is always constant. Infimum is always difference of between this is 4. So this 4. And infimum xt modulus of xt minus xt minus yt is 0. And infimum modulus of yt minus zt is also 0. So this infimum xt minus zt, this 4, this less than equal to 0 plus 0. So does not hold. 4 is not less than equal to 0. So triangle inequality is not satisfied for this definition dxy equal to this. So correct option is not metric. So this the other 1, 3 and 4 are all metric on C01. Next question 1b. Let y equal to the closed interval 1, 2 union open interval 3, 4. Consider y as metric subspace of the real line. Then correct option is 3. Closed interval 1, 2 is closed in y as well as open in y. Let y equal to this closed interval 1, 2 union open interval 3, 4. Then y dy is a subspace of the metric space Ru, where dy xy is the modulus of x minus y, xy belongs to capital Y. Now closed interval 1, 2, this equal to minus 2.5, 2.5, this open interval intersection y. This is the in the open sphere in the matrix space y dy. Actually, note this. Let y dy be a metric subspace of a metric space xd. Let a belongs to capital Y and r greater than 0. Then this open interval in for s dy center at A with radius R equal to open sphere, open ball SD at the point A with radius R intersection Y. This interval closed interval 1 2 is equal to this. Actually, this is SDAR. So center at this origin 0 intersection is an open sphere in the metric space y dy, and so closed interval this in open in y dy metric space, but not open in usual metric space over real number R, this closed interval. Again, 3 4 this open interval equal to this 3 4 intersection, open interval intersection capital Y is an open sphere in y dy. Hence, this open interval 3 4 is an open set in y dy, and 3 4 is also open set in Ru. So this closed interval, this third bracket 1 comma 2 and first bracket 3 comma 4 are such that one is complement of other. Hence, third bracket 1 2 and first bracket 3 4 are closed in y dy, because this the third bracket 1 2 is open in y dy. So these are complement. So obviously open interval 3 4 is closed in y dy. Again, this open interval 3 4 is open in y dy metric space. Then obviously complement of this 3 4 is closed interval 1 2 is uh, closed. So 1 2 closed interval and this 3 4 open interval are closed in y dy metric space, as well as and uh, open and closed, this both. Uh, so third bracket 1 comma 2 is closed in Ru, but 3 open interval 3 4 is open in Ru. Hence, third bracket 1 comma 2 is closed in Y, as well as open in Y. Next question, question 1C. Let X be an infinite set and D maps X cross S2 in union singleton set 0. N is the set of all natural numbers. Be a metric on X, then every singleton set in XD is corresponding is 3, both open and closed. Actually, by this definition, this D metric D X cross S2 in union 0, a singleton set, we consider this dxy, this k when x not equal to y, and this equal to 0 when x equal to y, where k is greater than equal to 1 belongs to the set of our natural numbers n, and xy belongs to capital X set. Actually, this metric is discrete metric on this set X, infinite set X. Now let R equal to half. Then for any A belongs to the set X, we get an open sphere. This at the point center at the point A with radius half. B A half equal is the set of all those X belongs to capital X, such that dxa less than half, less than half. So obviously this equals to the singleton set A. This equal to singleton set A, and so this shows that this singleton set A is an open set. Again, this singleton set is also called closed set. Hence, every singleton set in this metric space XD is both open and closed. Question 1D. Choose the set Y which as a subspace of R2 with usual metric is not complete. Correct option is 4. Y is the set of all those order pair 1 by m, 1 by n belongs to R2 such that mn belongs to the set of all natural numbers m. Here, this y, this subspace, this 1 by m, 1 by n, actually this first picks up m equal to 1, then running in. So 1 comma 1, 1 comma half, 1 comma 1 by 3, and so on. This. So for fixing up m equal to 1, and this is the sequence of points. This again m equal to 2, then 1 by 2 comma 1, and over the in 1 2 in 1, first m equal to 2 and then n equal to 1 2 up to n, then these points half 1 and this so on so on so on approaches to half 0. Consider the sequence this 1 comma 1 by n, and this sequence 1 1 1 2 1 3, and in y which is Cauchy sequence in y, and also in R2, and this sequence converges to 1 0 obviously, this sequence 1 0, but this does not belongs to y, because y is a set of all those 1 by n elements belongs to R2m and belongs to n. So this sequence cannot converge in y, but this Cauchy sequence. Hence y is an incomplete matrix subspace. And the complete matrix subspace requires a note that this complete space XD is said to be complete if every Cauchy sequence in X converges to some point of X. Next question 1E. The set x square by 1 plus x square such that x belongs to R is correct option is connected but not compact in a matrix space RDU. Actually, this S, let this given set is denoted by S. This is the semi-closed or semi-open interval. This 0 to 1. If we put x is the real number, if we draw the graph for this fx equal to x square by 1 plus x square by Desmos app, then we can find this picture. So 0 to 1 is the set numbers is equal to 0 to 1, and 0 is the closed interval including this set, remember, and 1 is open. So 1 is the limit point of the set. Clearly, this one is the limit point, but 1 does not belongs to X. Hence, S is not a closed subset of R. By Heinabler theorem for R, every closed and bounded subset of R is compact and vice versa. Hence, S is not compact in the matrix space RDU. And let fx equals to x square by 1 plus x square, x belongs to R. Clearly, f is a continuous function. F is a continuous function. And so, any 2 points of S, we always have a path connectedness. Hence, S is connected but not complete. But not compact, sorry, complete, not compact. Next question. If under the transformation W equal to 1 by Z, the image of the region Z equal to X plus IY, the set of all those G is Z, such that X greater than 1 is transformed into option 3 interior of a circle. W equal to 1 by Z, Z not equal to 0. Let Z equal to X plus IY and W equal to U plus IV. And from 1, Z equal to 1 by W. And so X plus IY equal to 1 by U plus IP, and this equal to U minus IP by U square plus B square. Comparing real and imaginary parts on both sides, I will get X equal to U by U square plus B square and y equal to minus by u square plus b square. Now it is given that x greater than 1. So when x greater than 1, so obviously u by u square plus b square greater than 1. So after simplification, we get this u minus half whole square plus b square each less than half square. So this in UV plane, complex W plane, and this is the UV plane. This is the sphere, the center at half comma 0, this point with radius half. This is the interior points, not equal. So this is the interior points of this circle, or points of this, and this the this plane x greater than 1 in the complex jet plane maps to in UV plane is this interior points of the circle. Actually, you can find this beautifully by this graph GeoAlgebra, and this is the jet plane. On the left hand side is the yellow color is the jet plane, and this is the W plane. So first we choose this line segment, and this transformation W equal to FZ equal to 1 by Z. You can change this. So this is the 1 by Z, and this is the point in the UV plane. This point is 1. This point is 1. And if you extend this line segment on this upper half portion, so this line in the UV plane, and this circle can be drawn in this way, red color. So is x equal to 1. This line is x equal to 1, and this lower portion circle, semicircle, this, if you extend this line and the lower portion of this I less than 0, then is the red color in the upper portion U plane. So, and now click point. So this point is x greater than 1. So this point mapped in the UV plane is this point. So press on this. So this is the region x greater than 1. So x greater than 1. So this portion is the mapped on this x greater than 1. So interior points of this circle in this UV plane. Next question. G. Let fz equal to mod z square into z. Z belongs to the set of complex numbers. Which of the following is true? Correct option is 1. F is nowhere differentiable in C. Now fz equal to mod z square into z. So this x square plus y square into x plus iy. So this x into x square plus y square plus iy into x square plus y square. So u plus ivc. So obviously u equal to x into x square plus y square, and v equal to y into x square plus y square. Del u del x, find del u del y, del v del x, and del v del y. Clearly, del u del x not equal to del v del y, and del u del y not equal to minus del v del x. Hence, f is nowhere differentiable in the complex plane C, and that is fz is not analytic on C, in C. Actually, this is the Cauchy-Riemann theorem. This fz equal to uxy plus ivxy is differentiable at the point z0, x0 plus i0. Then u and v satisfy the Cauchy-Riemann equation at the point z0, and that is ux equal to vy and uy equal to minus vx at the point z0 equal to x0, y0. Note that this condition is if f is differentiable, this implies uh, this imply is ux equal to vy and uy equal to minus vx at the point x0, y0. The Cauchy-Riemann equations satisfy, but not vice versa. Converse may not be true. So this condition actually is the necessary condition. This Cauchy-Riemann equation is the necessary condition for differentiability at the point z0 of f at the point z0. So contrapositively, we can write if Cauchy-Riemann equation does not satisfy this ux not equal to vy, y not equal to minus vx at the point x0, y0, this implies f is not differentiable at the point z0. So this condition is the necessary condition. Cauchy-Riemann equation satisfy this. This condition is but not sufficient condition. Next question 1h. Radius of convergence of the power switch summation j to the power 4n by 4n plus 1 is correct answer is 2, 1. And this series is this. Now for j equal to plus minus 1 and plus minus I, we get this j to the power 4n by 4n plus 1, put j equal to 1 or minus 1 or I or minus I, we get 1 by 4n plus 1. But this reach, summation 1 by 4n plus 1 divergence reach, because this 1 by 4n plus 1 less than 1 by n and 1 by n reach is divergence reach. So the given series is divergent for the points z equal to plus minus 1 and plus minus I. A n equal to 1 by 4n plus 1 from 1, and if r be the radius of convergence, then we know r equal to limit tends to infinity plus n by n plus 1. So this is equal to 1. Hence radius of convergence is 1 and the circle of convergence is the modulus of j is less than 1. And on the circle of convergence, the given series diverges at more than 1 points. Actually, there are 4 points. This 1, I, minus 1 and minus I. There are 4 points where the series is divergent. Next question I. What is the value of integration e to the power z dz z square minus 5z plus 6 over the integration mod z equal to 1? Correct option is 1. Now e to the power z square minus 5z plus 6 equal to fz, say we can write e to the power z minus 2 to z minus 3. Now this on this unit circle. Now z equal to 2 is here and z equal to 3 is here. 2 plus I0, 3 plus I0 on the complex plane. So fz is not analytic at this point z equal to 2 and z equal to 3. And these 2 points lie outside the circle mod z equal to 1. Hence by Cauchy theorem, integration of our C fz dz equal to 0. As fz is analytic inside on the curve C mod z equal to 1, and then we write this equal to 0. Last question J. What is the maximum possible number of fixed points of a non-identity Mobius transformation in C infinity extended complex plane? Correct option is 2. At most number of fixed points is 2. Consider a Mobius transformation. This Tz equal to Az plus B by Cz plus D. A, B, C, D are all complex numbers and C, D are not both 0. Let Z belongs to C be a fixed point of T, then Tz equal to Z. So from 1 we get Az plus B by Cz plus D equal to Z. And then after simplification we get cz square plus bracket d minus a into z minus b square b equal to 0. Case 1, if c not equal to 0, then c not equal to 0, then the equation is quadratic polynomial in equation. This is the quadratic polynomial in C, the quadratic equation in C. So left hand side is quadratic polynomial in C, and so can have at most two complex fixed points. This now tz equal to a plus b by z, a plus b by z, and c divided by c plus d by z. So t infinity, this equals to this b by infinity 0, c d by infinity 0, so a by c not equal to infinity. So infinity is not a fixed point in this case, that is when c not equal to 0. Case 2, if c equal to 0, then from 2 we get this d minus a into z minus b equal to 0. This the if subcases this one, if a not equal to d, then z equal to b by d minus a is only one fixed point of t. If d equal to a and b not equal to 0, then this t has no fixed point, because if a equal to d and c equal to 0, so a equal to d, c equal to 0, so we get tz equal to z plus b by d, and b not equal to 0. So t has no fixed point in this case. C equal to 0, a equal to d, may b not equal to 0. If a equal to d and b equal to 0, then both this a equal to d and b equal to 0 and c equal to 0. So we get tz equal to z identically. Actually, then this mapping is an identity mapping, and t fixes every complex numbers. There are infinite number of fixed points in this case. So infinite number of fixed points when c equal to 0, b equal to 0, and a equal to d. If c equal to 0, then t z equal to az plus b by d, then a by dz plus b by d. So when z equal to infinity, so a into infinity plus b by d, so this equal to infinity. Obviously, when c equal to 0, infinity is a fixed point. So c equal to 0, infinity is a fixed point, and then conclusion is that hence for non-identity Mobius mapping T can have at most two distinct fixed points in extended complex plane C infinity. Thank you for watching this video.